Hi, this is quick review to the joint distribution tables in functions and also the expected values. At the end, we're going to solve some problems as well. So we use the probability distributions in order to explain the behavior of some random variables. And when we've got the two random variables which are connected somehow with each other, we need the so-called joint distribution probability functions, which are going to tell us the probabilities for the different values of the two random variables. And in this case, we are going to call this as the joint distribution mass function. And as the same as before, we are going to define this using the tables or using the discrete functions. And again, the sum of all the probabilities, all the values for this joint probability mass function should be equal to the 1 in order to be the proper probability function. For example, let's consider, so let's roll two pieces of die. X is going to be the result of the first die. Y is going to be the result of the second die. Then we can create this kind of table for the joint values of these two dice. This table, so the X is going to take the values from 1 to the 6, Y is going to take the values from 1 to the 6, and the values inside this table here are going to be the probabilities depending on what's the value of the X and what's the value of the Y. For example, if the value of the X is equal to the 3, and if the value of the Y is equal to the 4, basically I'm asking you, hey, what is the probability that on the first trial you will get 3, on the second trial you'll get 4? This is going to be 1 over 6 multiplied to 1 over 6, and this is going to be equal to this value, which is 1 over 36, right? And we can fill this to all of the values for the X and Y. And please note that the sum of all of the values, all of the probabilities is equal to the 1 because there are 36 values and all of the values are equal to the 1 over 36. So in a continuous case, instead of just defining the density function as a single variable function, we're going to define it as the multivariable function. So now our function f depends on the two variables, x and y. And as we did before, so the integration of our density function over the whole region of the x, over the whole domain of the x and y should be equal to the 1. And in order to find the probabilities, we just need to integrate this 2 times for the value, for the range of the x and for the range of the y. The cumulative distribution function in this case is going to be the probability of x is smaller than specific value, small x, and y is going to be smaller than some specific value of the y. So this is the definition of the cumulative function, both for the discrete and the continuous case, depending on what, so in which case we're dealing with, we can find the probabilities differently. In a discrete case, we need to find the probabilities just looking to the tables. In a continuous case, we need to find the probabilities by integrating the density function. So the expected value in the joint distribution case is going to be very much similar as we did before. So before, let's say the expected value of the x multiplied to the y is going to be all values of the x multiplied to all different values of the y multiplied to the joint probability function, right? And so let's consider an example. So this is our table from the previous example. What I would like to find is the probability, so the expected value of the x multiplied to the y. And in order to do this, what we have to do is we need to get the one value of the x and go through all the values of the y and multiply this. Basically, x should be multiplied to the 1. So x1 multiplied to the y is equal to the 1 and multiplied. This is probability. X is equal to the 1 multiplied to the y is equal to the 2 multiplied to its probability, and so on. For example, if x is equal to the 1, y is equal to the 1, their probability is equal to the 1 over 36. It's going to be 1 over 36 in total. So if x is equal to the 2, y is equal to the 1, so I need to multiply the x and y, and then additionally to the probability, which is going to be equal to the 2 over 36. Or one of the other cases, what might be x is equal to the 4, y is equal to the 5. I need to multiply them, then multiply them to the probability, which is equal to the 1 over 36. In total, I will get 20 over 36. And in order to find the expected value of the x multiplied to the y, we need to find all of these combinations of the multiplications of the x and y and multiply them to their probabilities. So it's going to be slightly complicated, but we are going to do more easier example here. So in a continuous case, in order to find the expected value, we just need to doubly integrate the multiplication of the x and y to the adjoint density function in the whole region, on the whole domain of the x and y. So let's do a couple of problems. In the first problem, a bin of 4 transistors is known to contain 2 that are defective. So there are 4 transistors in a bin. We're going to choose one by one. And we know that there are 2 defective ones. So let's say N1 is going to be the number of the times we need in order to choose the first defective transistor, and N2 is going to be the number of the trials which we need in order to choose the second defective transistor. N2 is going to be the number of additional trials after we found the first defective one in order to find the second one. So in order to solve this problem, we are going to use the so-called box method. So in this box, I'm going to have 4 boxes. So the result of each trial. So I will choose one transistor by one. And whenever I choose the transistor, if this is defective, I'm going to denote this as 1. And if this is not defective, I'm going to denote this as 0. Defective as 1, non-defective as 0. So now let's consider what kind of values N1 and N2 can take. So the N1 can take, N1 is going to be the number of the trials until we choose the first defective transistor, right? So we know that there are 2 non-defective one and 2 defective. So the N can take the values 1, 2, 3. Can it take 4? No, because we know that there are only 2 non-defective transistors. Choosing the first defective transistor on the false trial would mean that we have all 3 non-defective transistors already in this box. So the N2 can take the values. N2 is going to be the number of the additional trials which we need in order to find the second defective transistor. So the N2 might take the values 1, 2, and 3, right? So in this case, for example, the value for the N1 is equal to the 1. The value of the N2 is equal to the 2. So we found the first defective transistor after the first trial, and we needed 2 more additional trials in order to find the second defective transistor. So we need to combine all of these cases. There should be 9 different cases of the combination of the N1 and N2, but only 6 of them are non-zero. So not all the combinations are possible. For example, I can't combine basically 3 and 3 here, right? Because I cannot choose like 6 transistors because there are only 4 transistors. So some of the combinations are going to be like impossible. So there are only 6 possible combinations. Let me write down all of them. So the first case is going to be, so what kind of combinations? So I'm going to draw the boxes. 6 boxes. 1, 2, 3. So I can choose the first defective and second defective like this. First defective, second defective like this. First defective, second defective like this. Or there are other 3 possible ways of choosing the 2 defective ones. It's going to be 0, 1, 1, 0, or 0, 1, 0, 1, or 0, 0, 1, 1. There are only 6 cases of the combination of the N1 and N2, which are going to give you non-zero probabilities. Let's find the probability actually. What is going to be the probability of this case? So I need to find, first of all, probability of choosing the first defective items. There are 4 items inside the box. 2 of them are defective. What is the probability of choosing one of them? It's going to be 2 over 4, right? So 2 over 4. We have to multiply this now. So we obviously do not do this. We don't put this back. So now there are 3 items, transistors left inside the box, and one of them is defective. What is the probability of choosing the defective one? It's going to be 1 over 3, right? It's going to be 1 over 3 multiplied. Now there are 2 non-defective ones. and I need two items left, and two of them are non-defective. What is the probability of choosing non-defective one? Is going to be equal to 100%. Multiplied as a 1, which is going to be equal to the 1 over 6. So probability in this case is going to be, again, 1 over 6. So we can quickly check this. It's going to be 2 over 4 multiplied to the, so 2 over 3 multiplied to the 1 over 2 multiplied to the 1, which is equal to the 1 over 6. And this is also going to be 1 over 6. This is 1 over 6. This is 1 over 6. And this is also 1 over 6. So there are six cases. All the probabilities are 1 over 6. And their sum is equal to 1. So everything is defined correctly here. So let's consider another problem to find the expected value of the joint distributions. So first, we are given the joint probability mass function like this. We need to find the expected value of the multiplication of the x, y, and z. So what we need to do is quickly, it's very simple. So the expected value of the x, y, and z is going to be a multiplication of all the values of the x, y, and z multiplied to their probability. Okay. So I'm going to basically find the multiplication of the three numbers, which is going to be equal to the 6, the multiplication of the three numbers, which is going to be equal to the 2, then 4, then 12. Then I'm going to multiply. So the x multiplied to the y multiplied to the z multiplied to the p of x, y, and z. In the first case, it's going to be equal to the 6 multiplied to the 1 over 4, right? So in the second case, it's going to be equal to the 2 multiplied to the 1 over 4. In the third case, it's going to be 4 multiplied to the 1 over 4. In the last case, it's going to be 12 multiplied to the 1 over 4. Then basically, I have to just sum them. It's going to be 6 plus 2 plus 4 plus 12, which is going to be equal to the 24, divided to the 4, which is equal to the 6. So the expected value of the multiplication of the x, y, and z, it appears is equal to the 6. We can find a different problem for the same joint probability mass function. We need to find the expected value of the xy plus xz plus yz. So we know that since the expected value is just a simple summation, we can just open the brackets and we can write this as the expected value of the xy plus the expected value of the xz plus the expected value of the yz. So finding the expected value of the xy, it means that just multiply the x and y. So we don't really care about what is the value of the z. So we multiply xy, 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 and xy. What kind of values we can have here? It's going to be 2 multiplied to these probabilities equal to the 4, because the multiplication of the xy is equal to the 2 on the first case, plus 2 multiplied to the 1 over 4, plus, in this case, it's going to be 4 multiplied to the 1 over 4, plus in the last case, it's going to be equal to the 6 multiplied to the 1 over 4. If you sum everything, it's going to be 14 over 4. So the expected value of the xz is going to be the multiplication of the x to the z. X to the z, x to the z, x to the z. So in the first case, it's going to be equal to the 6 multiplied to the 1 over 4, plus 2 multiplied to the 1 over 4, plus 2 multiplied to the 1 over 4, plus 4 multiplied to the 1 over 4. In this case, it's going to be equal to the, again, xz is, sorry, it should be 3 here, right? So 1 multiplied to the 3, 2 multiplied to the 1, 2 multiplied to the 1, 2 multiplied to the 2. It's going to be 11 over 4. And in the last case, we need to multiply the y to the z. So basically, say y to the z, y to the z, y to the z, y to the z. So in this case, it's going to be 6 multiplied to the 1 over 4, plus 1 multiplied to the 1 over 4, plus 2 multiplied to the 1 over 4, plus 6 multiplied to the 1 over 4, right? Okay, it's going to be 12 plus 3, which is equal to the 15 over 4. And then we just need to sum them all, because this is the expected value of the first case, this is the expected value of the second, this is the expected value of the third term. If we sum, it's going to be equal to the 40 over 4, or simply 10. So this expected value is going to be equal to the 10. Good. So this is how we need to calculate the expected value in a case of joint distributions. And our last two examples are going to be about the continuous case, the joint distributions in a continuous case. So we've got the function. We need to first of all find the value of the a, so that it's going to be a proper density function. We know that it is a proper density function whenever its double integration with respect to the x and y should be equal to the 1. So we just need to choose the value of the a in a way so that the double integration is going to give us the 1. So let's first of all integrate this with respect to the y. If we integrate this with respect to the y, and the whole domain of the y, so x minus 3 multiplied to the y dy from 4 to the 6, right? Its integration is going to be equal to a multiplied to the x minus 3 multiplied to the y square over 2 from 4 to the 6, okay? So let me multiply. So if I substitute the 6 instead of y, it's going to be equal to the 36 over 2 minus, if I substitute the 4 instead of y, it's going to be 16 over 2. It's going to be 36 minus 16 over 2, which is equal to the 20 over 2, or is equal to the 10. So basically, it's equal to the 10a multiplied to the x minus 3. After we've got the integration over the x. So now we have to do the integration over the x, over the y, sorry. So now we need to do the integration over the x. It's going to be integration of the 10a x minus 3 dx from minus 2 until 3. It's going to be 10a multiplied to the x squared over 2 minus 3x. We need to substitute the 3 and minus 2. So if I substitute the 3 here, it's going to be 9 over 2, which is 4.5, minus 9, which is going to be minus 4.5, right? Minus 4.5 minus 10a multiplied to, if I substitute the minus 2, it's going to be minus 2 in the square, which is 4. 4 over 2 is 2. Minus 2 multiplied to the minus 2 is 6 plus 6. 4 plus 6, 2 plus 6. It's going to be 8, right? It is equal to plus 6 and 2, 8. Good. So in general, I've got minus 4.5 multiplied to the 10 is going to be equal to the 45a minus minus 80a, and this should be equal to the 1. So it's going to be 125, right? So the a is going to be equal to the minus 1 over 125. Good. Yeah. In the last problem, we need to find the probability. So when the x is going to change from 0 to the 1, y is going to change from 4 to the 5. So our density function now looks like as 1 over 125 multiplied to the 3 minus x multiplied to the y. We first of all have to integrate this with respect to this. So this is 125, right? The value of the a. So we first of all need to integrate this with respect to the y. So its integration with respect to the y is going to be equal to the 1 over 125 multiplied to the 3 minus x multiplied to the y squared over t from 4 to the 5, because we need to find the probability of the y from 4 to the 5. If I substitute the 5, it's going to be 25 over t, right? 25 over t. If I substitute the 4, it's going to be 16 over t, which is going to be 9 over t, right? So this is going to be equal to the 9 over 250, because 9 over 2 multiplied is 1 over 125 is going to be 9 over 250 multiplied is 3 minus x. So now we need to integrate this. So 9 over 250 multiplied to the 3 minus x with respect to the x from 0 to the 1. So the integration is going to give you 3x minus x squared over 2. If I substitute the 0, it's going to be simply 0, right? If you substitute the 0 to both of the appearances of the x. Then if I substitute the 1, it's going to be 3 minus 1.5, which is equal to the 2.5, right? Or 5 over 2. So this is going to be equal to the 9 over 250 multiplied to the 5 over 2. So we can just substitute this. It's going to be 50. It's going to be 9 over 100. So the probability of x between 0 and 1 and y between 4 and 5 is equal to the 9 over 100.